I'm asking you to identify the scikit-learn hyperparameters that directly control the length scale setting within the radial basis function, RBF, kernel. This setting dictates how much each data point influences its neighbors. A small length scale means local influence, resulting in a wiggly function. Conversely, a large length scale suggests a smoother function where data points influence a larger area. Think of it like this. A small length scale is like whispering to only your closest friends, while a large length scale is like shouting to the whole stadium. This one's straightforward. The length underscore scale hyperparameter directly controls the length scale in the RBF kernel's equation. I'll explain the formula briefly. The kernel's output depends on the distance between data points and the length scale, which impacts smoothness. This hyperparameter, alpha deals with the noise level in your data. It doesn't impact how the distance between data points affects the function's smoothness. It's a totally separate setting. This one sets the limits, the upper and lower bounds, within which the length underscore scale can change. Think of it as the boundaries on a playground slide. The hyperparameter is the child sliding down, and this setting is the edge of the slide. It guides optimization but doesn't directly set the length scale. The new hyperparameter is used in different kernels, specifically, the Sklearn kernel. It's not used in the RBF kernel that you're studying here. This question asks you to identify the scikit-learn Gaussian process regressor's radial basis function, RBF, kernel hyperparameters that directly control the length scale. The length scale determines how far the influence of a data point extends. A small length scale means that nearby data points have a strong influence, resulting in a wiggly function. A large length scale means that points have a global influence, making the function smoother. Think of it like this. Imagine you're drawing a curve through some points. A small length scale would mean the curve changes direction very quickly near each point, whereas a large length scale means the curve is more smooth and gradual. We need to select from a list of hyperparameters. This is the key one. The length underscore scale hyperparameter directly sets the length scale in the RBF kernel's formula. Express x underscore I, x underscore j, squared, 2 asterisk length underscore scale squared. It's right there in the formula. Changing this value directly changes how the kernel calculates similarity between data points based on their distance. I think you got this. Length underscore scale underscore bounds don't directly set the length scale. Instead, they define the allowed range of values for the length underscore scale during optimization. Think of it like setting limits on a slider control. The optimization algorithm will search for the best length underscore scale value within these bounds. So it indirectly influences the final length scale used. Alpha represents the noise level in the observations. I would say it doesn't directly affect the length scale. The formula I just mentioned has nothing to do with it. Changing alpha changes how much the model accounts for noisy data, but not the spatial range of influence. Nu is a hyperparameter used with different kernels, like the Sklearn kernel, not the RBF kernel. It's completely irrelevant to the RBF kernel's length scale. I'm focusing on which scikit-learn's Gaussian process regressor hyperparameters directly control the RBF kernel's length scale, which governs the smoothness of the model's output. This is key to understanding how the model will generalize to new data. This one is straightforward. The length underscore scale parameter directly sets the length scale. It's the main knob you'll use to control how smooth or wiggly your model's predictions are. The formula shows length underscore scale squared in the denominator, so a larger length underscore scale means data points influence predictions over a broader range. A smaller length underscore scale leads to more local influence and a more intricate model. This doesn't directly set the length underscore scale. It's more like a guardrail. You're setting the allowed range for length underscore scale during the optimization process. It's essential for preventing the algorithm from finding unuseful length underscore scales outside of this range. Think of it as guiding the optimization algorithm to find a good solution efficiently. Alpha, which represents the noise level in your data, doesn't directly affect how quickly the influence of a data point decays in the RBF kernel. It's completely separate. This parameter belongs to different kernels, like the Sklearn kernel, not the RBF kernel. It's irrelevant here. I see this hyperparameter, lengthscale, as the heart of the radial basis function, RBF, kernel. It directly controls how far the influence of each data point reaches. Think of it like this. A small lengthscale means each data point only affects its immediate neighbors, resulting in a wiggly function. A large lengthscale, on the other hand, creates a smoother, more globally influenced function because each data point's impact extends further. The formula shows it clearly. The distance between two data points is divided by twice the square of the lengthscale. These bounds don't directly set the lengthscale. Instead, they act like guardrails during the optimization process. I think of them as setting limits on how high or low the lengthscale is allowed to get. The lengthscale will still be the key player in controlling the smoothness, but these bounds make sure the optimization process doesn't run wild and find values too extreme. I see ALPHA as a measure of how much noise is present in your data. Think of it as the level of uncertainty in your measurements. It affects how confident your model is, but not the spatial reach of influence of a point. That's what lengthscale does. This parameter, nu, is a hyperparameter that's used in other kernel types, like the Sklearn kernel, but it's not related to the RBF kernel we're focusing on here. So, we can safely ignore it for this problem. I see that lengthscale is the star of the show here. It directly controls how far the influence of one data point reaches. Think of it like this. A small lengthscale means each data point only whispers to its closest neighbors, creating a wiggly curve. A large lengthscale lets each point shout across the room, making a super smooth curve. That's because the lengthscale parameter appears directly in the RBF kernel formula. It's in the denominator of the exponent, controlling the decay rate of the kernel's output. It's the length scale, VOMC. Now, lengthscale are like guardrails for lengthscale. They don't directly set the lengthscale value, but they keep it within a reasonable range during the optimization process. Think of it as keeping the model's search for the optimal lengthscale within a specified range. It helps avoid searching in unrealistic areas that may result in non-convergent or unstable solutions. So, while it doesn't dictate the value, it impacts the result. Parameter ALPHA is about noise. It describes how much random error or uncertainty we expect in our data. A larger ALPHA means we believe our data is noisier. It doesn't affect how far the influence of a single data point extends. The NU parameter is for different types of kernels, not the radial basis function, RBF, kernel we're focusing on here. It's not relevant to our current problem, so we'll leave it aside for now. I see lengthscale as the star of the show. It directly controls how far the influence of one data point reaches in the radial basis function, RBF, kernel. Think of it like the radius of a bubble around each data point. A smaller lengthscale means tighter, more localized bubbles, while a larger one creates broader, more overlapping bubbles. This directly affects how smooth or wiggly your model's prediction curve appears. Now, ALPHA is a different beast altogether. It doesn't control the bubble's size, instead, it handles the noise level in your data. Imagine sprinkling salt on a smooth surface. ALPHA represents the amount of salt, more noise, making the surface less smooth. It doesn't change the size of the bubbles, the influence of data points. Let's move on to NU. This one's a bit of an outsider. It's not directly related to the RBF kernel. It's a parameter for other kernels like the Sklearn kernel, so we can safely ignore it in this context. It's like showing up to a party for the wrong friend. Finally, lengthscale sets limits for lengthscale. I think of it like a fence around a playground. It doesn't tell you where to play, but it confines your options. The optimization process for finding the best lengthscale will stay within these bounds, ensuring the value remains within reasonable limits. The radial basis function, RBF, kernel is a mathematical function used in machine learning, specifically within Gaussian processes to model relationships between data points. I consider it a critical component for measuring similarity or distance between points. It plays a critical role in creating smooth predictions and estimations. I can explain ALPHA in a different way. In the context of Gaussian process regression, alpha represents the noise inherent in our observations. It is a regularizing parameter which indicates how much we trust the observations. A larger value of alpha indicates that we believe that there's a lot of noise in the data, while a smaller value would mean the opposite. A Gaussian process regressor is a type of regression model that uses Gaussian processes to predict outcomes. This is a powerful tool for machine learning that is built upon the core concept of a Gaussian process and the underlying functions, such as the RBF kernel. I'm talking about a machine learning model from the Sklearn library. It uses Gaussian processes to predict continuous values. Think of it as a sophisticated way to do curve fitting. It's pretty cool because it gives you not only a prediction but also an estimate of how uncertain the prediction is. This is a key parameter in the radial basis function, RBF, kernel, which is a way of measuring the similarity between data points. A larger length scale means that distant data points still influence each other strongly, leading to a smoother prediction. A smaller length scale means that only nearby data points heavily impact the prediction, resulting in a more wiggly prediction. These set the limits within which we can optimize the length scale. It's like saying, okay, optimizer, don't search for a length scale smaller than this or larger than that. We define these bounds to make sure the optimization process doesn't go haywire. This parameter belongs to other kernels and not the RBF kernel. It doesn't apply here. This represents the noise level in the data. It's essentially how much uncertainty we expect in our observations. This doesn't directly control how far the influence of each data point reaches. This is short for radial basis function kernel. It's a function that measures similarity between data points based on the distance between them. The formula is like this: k, x, x, equals express, xx, squared, 2 asterisk length underscore scale squared. In simple terms, the closer 2 points, the more similar they are and the greater the value. Think of it as measuring how close 2 points are in feature space. This parameter is not relevant for the RBF kernel. This parameter controls the noise in the data points. It's a measure of how much random variation there is in the measurements. This is the hyperparameter directly controlling the smoothness and range of influence of the RBF kernel. A small length underscore scale implies that only nearby data points affect the prediction, while a large one means that data points far away also strongly affect it. This is the core question of this problem. It's asking you to identify which settings directly control the reach of influence of each data point when predicting. In simple terms, you're given a model that predicts continuous data and you want to adjust its parameters to improve its accuracy.